Hello, my name is Benjamin Cady. I am the project manager on the GW Engineering team, and today our team will be presenting the final design of the Shaw Lane reconstruction and Shaw Power Plant renovation projects. Members of our team can be seen below. Firstly, Greenaway Engineering would like to extend our deepest gratitude to the faculty of the Michigan State University Civil and Environmental Engineering Department and the industry professionals who have volunteered their time to make this project possible, despite significant unorthodox circumstances such as a global pandemic. It is because of their sacrifice that the betterment of young professionals is made possible during these trying times. We would like to express special thanks to the following individuals who helped our team on this project. This presentation summarizes the renovation and reconstruction of infrastructure on Michigan State University campus. These improvements to campus primarily address the guidelines laid out in the 2020 MSU Campus Master Plan. The image displays a satellite image of campus in reference to the area of study proposed for this project. The project is divided into two primary components. First, a new STEM building is to be constructed surrounding the now decommissioned Shaw Lane power plant. Second, North Shaw Lane will be closed permanently and replaced with a dedicated bicycle pathway, while South Shaw Lane will be widened to accommodate the removal of North Shaw Lane. Lastly, new green spaces will be added to campus in place of existing parking lots within the study area, along with the new stormwater water management systems to provide natural buffer zones in the event of flooding, as well as filtration for contaminants entering the Red Cedar River. The university will keep the health and safety of the public of primary concern during this project. The construction of a new STEM facility is detailed in the 2020 MSU Campus Master Plan. There are several primary issues not mentioned that the new STEM building also addresses, including increases in STEM enrollment. According to data provided by MSU, the number of STEM-related credits taken by MSU students per semester increased from 422,000 to 599,000 between 2006 and 2016. A second issue that the facility addresses is the aging nature of the existing infrastructure available to students in STEM majors. Most facilities, including the engineering building, are nearly 40 years old and have been proven to show structural signs of degradation. Lastly, there has been an increasing issue of classroom shortages throughout campus. Additional study spaces in classrooms are necessary to keep up with increased enrollment. The reconstruction of Shaw Lane will address several existing problems on campus as well, including the first being a need for increased green infrastructure to reduce the levels of carbon emissions on campus. This was accomplished by the addition of a dedicated bicycle pathway in place of North Shaw Lane. The addition of this pathway will make zero emission travel much easier on campus and reduce the amount of personal vehicle transit, potentially also increasing the use of public transportation. The new STEM building will also largely affect the local traffic levels due to an increased number of students and faculty using the facility. A second issue that the reconstruction addresses is the need for additional green spaces that will serve many purposes. The goals and objectives of this project primarily revolve around the addition of green infrastructure as well as needs for a growing campus. More specific requirements include the completion of various elements of preliminary design for both the new STEM facility and the reconstruction of Shaw Lane. Prior to construction, the existing conditions of the project site contained Shaw Lane Power Plant, which was formerly used for steam power on campus. The smokestack seen in the image has the letters MSC painted on it. It stands for Michigan State College, which is what the university was known as during the construction of this facility. The power plant was decommissioned in 1975 and lay dormant until 2011 when the accompanying smokestack was demolished. The site has been unused since that time. The existing conditions of the area immediately surrounding the Red Cedar River have several issues as well, including annual flooding in spring and a low river water quality due to reasons that our hydrology specialist will specify. The interdisciplinary tasks conducted during this project were necessary for a successful outcome. Several design considerations were considered for alternative designs, including solar roofs or a smart water collection system. The stormwater management system design required important interaction between our hydrology, transportation, pavements, and environmental specialists regarding various effects of runoff. Other interdisciplinary actions included certifying construction materials with an environmental specialist to ensure there is no unintended contamination of local ecology. And of course, all deliverables were submitted to the project manager. Without further ado, I'll pass it off to our first technical specialist, Owen Brenneman.
Hello, my name is Owen Brenneman. I am the structural specialist representing GW Engineering for the Michigan State University Shaw Lane Power Plant renovation project. As part of the MSU 2020 Vision Campus Master Plan Report, a new academic building is envisioned at the location of the now decommissioned Shaw Lane Power Plant. The structural component of this project was to build a 4-story academic building addition to the existing power plant building, with a 1-story basement consisting of 2 main structures connected by a 5-story walkway. The scope of this project did not include any work on the existing power plant building. It's worth mentioning that the other members of my team played an important role in my final structural design. For example, the hydrology specialist and I discussed whether or not to include a green roof on the top of the structure to help with drainage in the area. And although it didn't make it to the final design, it was considered in the conceptual design phase. The environmental specialist also offered some advice on sustainable elements to incorporate in my design, as well as made sure I wasn't using any hazardous materials in my structure that would be harmful to the soil and water underneath. I was also in constant contact with my project manager, updating him on my progress, as well as receiving feedback on my progress reports. Overall, feedback from the entire team was crucial for my design. To begin the design, some requirements were to be met. The architect proposed an L-shaped footprint for the building to be wrapped around the existing power plant in one of 2 locations. The architect also provided requirements for building dimensions, building height, dedicated space allocation broken up by floor, number, and size of room types, as well as materials and the type of structural frame to be used. The L-shaped structure was chosen to be wrapped around the southwest corner of the existing structure based on cost savings and time considerations. The original dimensions proposed by the architect went unchanged as they were perfect for the design beam spans. The final structure will stand 65 feet tall with a 15-foot roof and a 12-foot basement level. All space allocation requirements were met, and we were even able to increase the square footage of almost every room type without exceeding the 75% maximum dedicated space limit. This will be a steel frame structure featuring brace frames as well as moment frames, and will consist of concrete slabs and exterior walls. These features and materials were chosen based on various sustainability and public interest considerations. This structural design adheres to the codes, standards, and regulations provided by ADA, IBC, MBC, ACI, AISC, ASCE7, and FEMA. Both structures are identical as far as beam and column placement, except for the additional 40 feet in structure A. All 80-foot frames were broken up into 2 exterior 30-foot spans and 1 interior 20-foot span. All 160-foot frames were broken up into 5 equal 32-foot spans, with the additional 40 feet of structure A broken up into 2 equal 20-foot spans. Level 1 of each structure features a 12-foot ceiling height, while levels 2 through 4 and the basement level of each structure feature a 12-foot ceiling height. Like I said before, all space allocation requirements were met and exceeded. Here you can see a table of the final room quantities categorized by room type, area, and number of each room type. And I have provided 2 of the 5 plan drawings produced for the proposed architectural layout. Once the structural layout was finalized, loads and load combinations which the structure would have to withstand were identified. The load patterns used here were dead load, live load, wind load, snow load, and roof live load. The load combinations used here included combos 1 through 3 from the ASCE 716. SAP 2000 was the software used to model the structure as well as these loads to analyze how the structure would deform and resist. Some final loads experienced by various members in the structure, as well as a deformed shape found by running the analysis software, are given here. Using the loads taken from the analysis, 6 typical members were identified for the design based on their maximum load cases and location throughout the structure. These members consisted of 2 columns, one high strength and one low strength, 2 beams, 1 short span and 1 long span, 1 truss member, and 1 bracing member. In doing so, we were able to provide a cost and time-efficient conservative design. A table of the typical members chosen and their loads are provided here. Utilizing the design forces that were chosen along with the AISC steel manual and the skills taught in MSU's steel construction design course, I was able to perform safety checks and ultimately design steel sections for each of the 6 typical member identified here. Those safety checks, also called limit state checks, involved mathematically ensuring that certain members were able to avoid common failure patterns under the applied service loads defined previously. Here I have provided a table of my final typical member sections along with a figure of where each will be located in the frame on this next slide. Once member sections were chosen, a cost estimate could be produced. The cost estimate shown here lists item types, total quantities, total costs, quantity and cost factors applied, a total cost of each structure, as well as standard project fees applied, and ultimately shows in red the final cost of the proposed structure. The next steps in the design phase are to design typical members and connections, slab sections, exterior wall sections, and to create a fireproofing plan. After these items are finalized, a construction plan must be produced as well as a project schedule. Lastly, before construction, the contractor chosen must apply for construction permits through the City of East Lansing and Michigan State University, such as use of street, water, and sewer connections, and special transportation permitting. Now I will hand it over to Haley, our hydrology specialist. Thank you.
My name is Haley Lewis, and I am the hydrology engineer for G&W Engineering. I have been tasked with redesigning the stormwater sewer management system on the project site. The goals and outcomes of the project are to be aesthetically pleasing and fit with the rest of MSU's campus, to incorporate low-impact design features, to prevent flooding of campus and downriver, and also to prevent further deterioration of the water quality of the Red Cedar River. Some inadequacies that are faced by Michigan State University and are addressed in the design are flooding during the wet months, especially in March and April, and also the fall. Both pollution entering the Red Cedar River and stormwater runoff having high pollutant concentrations are big issues faced by campus due to the amount of development, fertilizers used, and also pollutants collecting on impervious surfaces, which are then washed away during storm events directly entering the Red Cedar River. There is also a minimal amount of open and grass areas on campus and excessive runoff from impervious surfaces. On the left is an aerial view of the entire project site, and on the right is a zoomed in view of the east half of the project site. The stormwater system that was designed was only for the east half of the project site. The west half was chosen to be left alone because the existing infrastructure meets regulations and codes, and there will also be no development on that part of the project site. The low impact design features chosen to be used are retention basins and bioretention areas. The retention basins accommodate a 24-hour, 100-year storm event, and there will be 2 of them. The bioretention areas act as natural buffers as well as naturally treat water from storm events and any runoff. This is representing a conceptual design of the stormwater system. The catchment areas are represented with pink, and were divided up using the topography and ground coverage. In each of these catchments, either an inlet, a culvert, or a manhole was placed. They were placed at the lowest elevation of each catchment. From there, a pipe network was used to connect all of these inlets. The resulting pipe networks can be seen here in blue. There are 3 of them labeled A, B, and C. Networks A and B enter and drain into the retention basin located next to the existing and extension of the Shaw Lane Power Plant building. Network B drains into the second retention basin, which is located across the street from the building in front of Wells Hall. Green areas are also going to be used and represent the bioretention areas as well. These were implemented throughout the project site to add in open spaces and try to address the inadequacies faced by campus. Calculations were done using the rational method. This was done to find the size of the pipes, the velocity through the pipes, and also the flow rate of each one. The results meet Ingham County Joint Commissioner Code as well as regulations for Michigan State University. The table summarizes the cost analysis for the new stormwater sewer management system. It includes materials such as the inlets, culverts, and manholes, as well as the sewer pipes. It also includes excavation and backfilling and the low impact design features. Additionally, an engineering design fee was added to the cost, totaling approximately $5.6 million. Thank you, and I will now pass it off to Gary for pavements.
Hello, everyone. My name is Tianze Gao. I am a pavement specialist from the GW engineering team. In CE 495 Senior Design Project, my primary work is improving Shaw Lane Road and Red Center Road pavement conditions. Here is a map view of our project. Shaw Lane Road is the horizontal one, and Red Center Road is the right vertical one. Moving to my design procedures. Firstly, the GW engineering team needs to collect fundamental data. The fundamental data includes resilient modulus, design traffic data, climatic condition, and the regulations adopted for the project. First, resilient modulus is a fundamental material property used to characterize unbound pavement materials. It is a measure of a material stiffness and provides a mean to analyze the stiffness of a material under different conditions, such as moisture, density, and stress level. We assume a sand sample base under the pavements, and resilient modulus is between 3,000 to 4,000. Next is design traffic data. ESO represents a mixed stream of traffic of different axial loads and axial configurations predicted over the design or analysis period, and then converted into an equivalent number of 18 kits single axial loads summed over that period. I received some help from our traffic specialist Joey. He provided me the detailed traffic count data. Then I calculated the ESOs for different roads by using ESO equation. Then we gathered climatic condition data by using long-term pavement performance (LTPP) web-based tool. We also found the PG grade as 58 minus 28 by combining our traffic data. For local standards, based on MDOT pavement design procedure and policies. This project design life should be 20 years. Minimum thickness for various pavement are differentiated by gradation. All permanent pavement designs should include at least one lift of either 19 mm HMA or 25 mm HMA. For rigid pavements, all rigid designs will consist of a minimum of 10 inches plain concrete and a minimum 2-inch layer of flexible pavement over a base course. The lane width of this project is 12 feet. Next, GW engineering team provided 4 different reconstruction and rehabilitation alternatives. They are new flexible pavements, new rigid pavements, AC overlay, and milling and filling. This is a sample design. AC overlay for eastbound on Shaw Lane. Based on AASHTO recommendations, we choose 0.17 as layer coefficient of asphalt layer, 1 as drainage coefficient. Structure number is 0.9. For aggregate base, layer coefficient is 0.14. Drainage coefficient is 1. Structure number is 1.1. For subbase, layer coefficient is also 0.14. Drainage coefficient is 1. Structure number is 1.1. Then we will do a 2.1-inch overlay on the original pavement surface. This is a table of initial cost for different roads and different design alternatives. The lane widths are all 12 feet. And the November asphalt price is $392 per ton. Concrete price is $140 per ton. The results are shown in the table. We can observe that AC overlay is the most cost-effective alternate, and eastbound on West Shaw Lane has the highest value. This is caused by the road condition. Eastbound on West Shaw Lane normally has higher traffic volume than others road, and Red Center Road was reconstructed recently, so there is not much work for it. Life cycle cost analysis (LCCA) is a method of assessing the total cost of facilities ownership. It takes into account all costs of acquiring, owning, and disposing of a building or building system. LCCA is especially useful when project alternatives that fulfill the same performance requirements but differ with respect of initial cost and operating cost. And they have to be compared in order to select the one that maximizes the net savings. LCCA is very suited for our project. In this table, AC overlay has the lowest EUAC. And in this way, GW engineering team presents AC overlay for the Shaw Lane Road and Red Center Road as the final recommendations. The total length of West Shaw Lane is 0.7 miles, and there are 4 lanes in 2 directions. The total length for Red Center Road is 0.5 miles, and there are 2 lanes in 2 directions. Then we calculate the capital cost based on the previous initial cost. The final capital cost is $991,310. Next, please welcome our next presenter, our traffic specialist, Joey.
Hi, my name is Joey DiCristofaro. I am from the suburbs of Chicago, attending MSU from fall 2016 to fall 2020 in hopes of earning a Bachelor of Science in Civil Engineering degree. I took on the transportation role for this project and I'm a part of the Green and White engineering team. The Shaw Lane Power Plant Reconstruction and Renovation Project consists of a new academic building that was envisioned at the location of the decommissioned Shaw Lane Power Plant. Plans are to renovate the existing building and add a substantial expansion to the building footprint. The segment of Shaw Lane between Chestnut Road and Red Cedar Road will be repaired, as well as the closure of North Shaw Lane and conversion of South Shaw Lane to a 4-lane, two-way road. Implementing a coordinated bicycle system with dedicated pathways and sidewalks for pedestrian traffic on North Shaw Lane. And new design criteria must prioritize pedestrian traffic, bicycle lanes, and mass transit vehicles like the Catibus that we have on campus, all in hopes of reducing private vehicle miles on campus. MSU 2020 vision really focused on implementing green infrastructure, providing a suite of transportation options that maximize the movement of people and minimize the movement of cars, reducing vehicle miles traveled, as well as reducing greenhouse gas emissions, designing all roads as complete streets, so designed and operated to enable safe, attractive, and comfortable access and travel. Want to promote efficient land use that protects existing and creates new green spaces on campus. Establish a coordinated bicycle system, so bike lanes within roadways, dedicated pathways, and shared use pathways. Here you can see a satellite photograph of the proposed site and study area. The project site is located north of West Shaw Lane and west of Red Cedar Road in East Lansing, Michigan. The overall study area is the segment of Shaw Lane between Chestnut Road and Farm Lane. The proposed development will consist of a 117,000 square foot, $100+ million STEM teaching and learning facility, 2 new proposed green spaces in between the existing North Shaw Lane and South Shaw Lane, each with about 70,000 square feet each, 140,000 square foot in total. In order to implement the new green space on campus, the removal of parking lot 40, which is the faculty lot, and parking lot 39, which is the consumer visitor lot, was deemed necessary. The removal of these parking lots will eliminate a total of 549 parking spaces on campus. Parking lot 56 is located south of West Shaw Lane and west of Red Cedar Road. This is currently a 1-story parking lot, but may be converted into a multi-level parking garage in order to fulfill some of the lost parking stalls in lots 40 and 39. Here you can see the level of service for intersection of Shaw Lane and Red Cedar Road. All the traffic data was found on the Tri-County Regional Planning Commission traffic count database system. Using Syncro to analyze the new intersection design, the level of service for each approach can be found. The level of service is based on the peak hour of traffic based on the number of lanes at the intersection, traffic volumes, and traffic control. Level of service classifications are based on driver discomfort, driver frustration, fuel consumption, and lost travel time. The worst level of service appropriate for a local road in an urban environment is a level of service D. As you can see from this table, you can see the level of service for each approach, the overall intersection level of service, as well as the overall intersection delay, and all the level of services are B or greater, which is good. Here is a picture of the existing intersection design. And here is 2 pictures. That on the top is the existing intersection design, and on the bottom, the new intersection design is shown for comparison. In this picture, you can see the 2 new proposed green areas where parking lots 39 and 40 were, as well as the conversion of North Shaw Lane into a pedestrian bicycle lane only. In this image, you could just see a snippet of basically the location that I was mainly focused on redesigning. Here's a close-up of that location. You can see the new intersection design for Red Cedar Road and Shaw Lane, as well as the traffic lane configuration, the channelization for each turning lane, and the lane widths for each road. The lane widths are all 11 feet. In this table, you can see the cost estimates specifically for the transportation side of this project. Overall cost estimated to be just under $3 million. Some ways to reduce the cost of this project would be to reuse the existing traffic control devices like the mast arm and strain pole, if applicable, as well as the various traffic signs posted throughout campus, like the speed limit signs and the no right or left turn on red signs. This table shows the transportation design schedule plan. So plans are to start design on September 1st of 2020 and construction hopefully ending around June 30th of 2021. Here are some alternative design ideas. First one was a roundabout intersection. Positive is the level of service for vehicles for a roundabout is typically good, but a big disadvantage would be for the pedestrian traffic. Another design option was a pedestrian bridge or tunnel that went over or under Red Cedar Road. Positive to this would be, it'd be beneficial for pedestrian traffic, but big negatives, it would cost a lot, it'd be very expensive, and it would also obstruct entrances to multiple buildings, for instance, the International Center and the new Shaw Lane Power Plant building. Instead of constructing a pedestrian bridge or tunnel, an unsignalized crosswalk was a potential solution for pedestrians to use while crossing over the north part of the intersection of Shaw Lane and Red Cedar Road, but this will cause problems with the level of service of the road as well as pose a hazard to pedestrians, as this would not be a safe location for this type of crosswalk, especially due to the heavy load of pedestrians expected to use this crosswalk. In order to safely implement a route for pedestrians and bicyclists to traverse this intersection, the pedestrian bicyclist pathway on North Shaw Lane will be redirected to the southern part of Shaw Lane where the intersection will now be. This will enable a safer way of travel for both pedestrians and cars traveling throughout this intersection. So it is recommended to have this type of phasing and geometric design because it allows the safest route of transportation while also allowing for the highest level of service attainable for each intersection approach. It is also recommended to have 11-foot lanes as to allow the larger buses and trucks to easily traverse certain turns that wouldn't be traversable with 10-foot wide lanes. The phasing for left turn and right turn is permitted in order to ensure an acceptable level of service while also taking safety into consideration. Thank you for your time.
Hi, everybody. My name is Colin High.
Hi, my name is Jerry Xu.
And we are the environmental specialists for G&W Engineering. We worked on one small project related to the Shaw Lane Power Plant regarding some soil contamination that was found there. And we worked much more in depth on a different project that was related to the coronavirus. So first we're going to go over the PCB contamination at the Shaw Lane Power Plant site.
The company Swanson Environmental investigated the PCB contaminated soil at the former power plant site. In the vicinity of the concrete pad, with an area of 85 feet long and 40 feet wide, the range of PCB concentrations was up to 1,100 ppm and exceed 100 ppm. At the south of the power plant building, with an area of 120 feet wide and 90 feet long, the range of PCB concentration was up to 420 ppm and exceeds 50 ppm. So the results from two major areas of PCB contaminated soil conclude that the PCB concentration around the power plant was higher than the Michigan Environmental Response Act 307 Type B cleanup calculation for soil, which is 1 ppm. In addition, based on Section 40 CFR 761.6 of the Toxic Substance Control Action, the soil contamination equals or greater than 50 ppm should be incinerated or disposed at the landfill.
So the information that we have on the site is based on numerous soil borings that were done, as well as 5 monitoring wells. The monitoring wells did not detect any PCB contamination, so we believe that all of the contamination is in the soil. Now there is a large amount of soil between 1,200 and 2,000 cubic yards that is contaminated with a low amount of PCB, but it is still over 1 parts per million. There's a smaller but still significant amount, around 300 to 375 cubic yards of soil with a concentration greater than 50 parts per million. As Jerry mentioned, the two options we have are incineration or placing the soil in a hazardous waste landfill. And in this instance, it makes more sense to excavate all of the soil that was greater than 1 parts per million with contamination and sending it to an appropriate landfill facility. That's because of the large volume of the waste, as well as the relatively low average concentration. It just would not be worth it to incinerate this large quantity of soil with a relatively low concentration of PCBs. So next we're going to discuss the coronavirus project that we worked on. We were looking at SARS-CoV-2 RNA behavior in wastewater treatment plants. The focus of our project was on wastewater-based epidemiology. This is a relatively new field, and it is the process of sampling and testing sewage in order to gather information about the population that is releasing waste into said sewer. So by testing sewage, we can gather a variety of information. The technology has been used to monitor illegal drugs, monitor legal drugs, monitor some other bacterial levels. But what we want to look at, or what there's a lot of study being done right now, is using this technology to monitor coronavirus rates. For example, by testing influent water at a wastewater treatment plant for a city, based on the concentration of virus RNA, we could hopefully determine approximately the number of cases that are currently in the city with active coronavirus. Or it could also be done on a smaller scale. For example, testing sewage from a college dorm could reveal if any or multiple students had coronavirus. But unfortunately, there are a few things that need to be researched before this approach is viable and accurate. One of which is the decay and behavior of the viral RNA in wastewater. So we were doing research on this field by modeling 2 real-life plants, and we were focusing on the behavior in wastewater treatment processes, specifically conventional activated sludge and oxidation ditches, to see how the virus reacted to those environments.
So from the literature review, the decay of non-enveloped virus is not well understood. However, the primary factor that influenced SARS-CoV-2 RNA decay was found to be the temperature. In general, the higher temperatures increase decay rates, especially at 20 degrees Celsius and above. Other factors include pH, medium, and wastewater treatment process also influence the SARS-CoV-2 RNA decay.
So modeling was done in a software program called Sumo. I modeled the city of Williamston, Michigan wastewater treatment plant. The city of Williamston uses a conventional activated sludge system for their secondary treatment, meaning that after the water has already flowed through some treatment, it gets to the conventional activated sludge process, which consists of an aeration tank where chemicals and bacteria are added to process any organic waste in the water. And then it flows to a clarifier where those solids can settle out. The two biggest factors that I found to affect the virus removal were the detention time and the rate of the flow rate of the return activated sludge. So the detention time is dependent on the flow rate of water through the plant. At low flow rates, the water spends more time in the aeration tank in the clarifier, giving it more time to break down naturally. At lower temperatures, this didn't really have any effect because the change of 1 versus maybe 2 days doesn't really have hardly any effect when the decay rate is so low. But in warmer climates, a longer detention time led to a significantly decreased concentration of virus in the effluent water. The other factor was flow rate of the return activated sludge. The solids that settle out of suspension in the clarifier, that material is known as sludge. And according to our simulations and everything, a lot of the virus ends up in this sludge. So therefore, the sludge has a very high concentration of virus RNA. Now, traditionally, some of the sludge is pumped back to the head of the aeration tanks and back into the water in order to add bacteria. But in this case, when you're adding this high concentration of virus in the sludge to the water, it raises the overall concentration of virus in the water and also in the effluent water that is leaving the plant. So by decreasing the amount of return activated sludge used, the effluent water would have a lower concentration of virus from the conventional activated sludge system.
The oxidation ditches were created in Sumo based on the real situation, the Mason's water reclamation plant at the Ohio State. The wastewater treatment plant has 2 oxidation ditches with a capacity of 5.6 million gallons per day for each oxidation ditch, and each oxidation ditch includes 3 treatment rooms, which are anaerobic room, an oxys room, and an aerobic room with different levels of oxygen. And also the detection time is between 16 to 27 hours for wastewater treatment. In addition, the oxidation ditches are typically used in junction with the secondary clarifier to precipitate activated sludge solids, and then some of solids are returned to the first anaerobic room as return activated sludge process. The result of virus inactivation tendency at the effluent was come up at different decay rates under 4 temperature conditions. The result indicates that it works for the oxidation ditches treatment process to remove SARS-CoV-2 RNA in the wastewater. And there is a rapidly decreasing from low temperature to high temperature, especially during 0 to 10 days. Also, at different decay rates, the maximum, average, and minimal values of virus inactivation also reflect the same result. Higher temperature at 37 degrees Celsius has lower virus inactivation compared to the lower temperature at 4 degrees Celsius. Conclusively, higher temperatures with high decay rates lead to more efficient virus removal. As a consequence, all results related with different temperature conditions prove the conclusion from the above literature review. Furthermore, the different virus concentration at the infant also influence the result of virus inactivation at the effluent. The tendency of virus inactivation with different virus concentration shows that there is a decay for the virus. So from 1 to 100 RNA copies per 100 millimeter, the range of the average remaining virus from 0.03337 to 1.04 RNA copies per 100 millimeter. So the larger concentration leads to more remaining virus at the effluent. However, there is an increase of virus inactivation at the virus concentration of 100 RNA copies per 100 millimeter. So this situation may be caused by large virus concentration at the infant, which means that a higher concentration condition corresponds to a longer stability of the virus in the wastewater. In addition, the presence of organic matter and oxygen in the wastewater has a positive impact on the virus survival. So the virus in the high oxygen zone can continue to reproduce. So this is why there's an increase of the virus inactivation. Thank you.